welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings, or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Good morning, good afternoon, wherever you may be. I would first like to take this opportunity to welcome you to this exciting presentation. How can reliable electro-optical S-parameter tests improve your optical transmitter and receiver designs? This presentation is part of a webcast series covering two tracks, digital and photonics. The digital track covers topics around high-speed digital test challenges, and the photonic track is focusing on 40-100G optical networks and components. There are more live and recorded events on our webpage, which you can find the complete schedule at www.agilent.com/find/DPT webcasts. The event today discusses time domain measurements, which give a fairly good impression on the quality of optical transceivers. However, when it comes down to troubleshooting issues in your design and components, then the time domain has its limitations. This webcast describes the principles of frequency domain S-parameter measurements on electro-optic components and gives us cases of transmitter components, detectors, and PIN TIA receivers, including on-wafer measurements and measurements on 750 HM components for CaTV applications. Further examples for measurements on opto-electronic components with balanced electrical ports and under various optical and electrical operating conditions will be given. The presenter for this presentation is Hansjoerg Haisch. Hansjoerg is the R&D project manager for Agilent Technologies' Photonics product line. He leads development teams that focus on test and measurement solutions for photonic component and transmission test. One of his recent product introductions was the Lightwave Component Analyzer family for opto-electronic S-parameter testing. Hansjoerg holds a Ph.D. from Stuttgart University and a Master of Science from Oregon State University, both in electrical engineering, and he is one of the worldwide experts in optical telecommunications and optical component testing. A couple of important items before we begin today's presentation. Please feel free to chat your questions at any point throughout the presentation. Please chat directly to Oliver, and he will be sure to forward your questions on to Hansjoerg. We will address all your questions at the end of the presentation. If by chance we are unable to answer all of the questions, Hansjoerg will follow up after the presentation via email. Should you have any questions after the presentation is complete, you can email Hansjoerg directly, and I will post his email address in the chat box. If you could take a moment to fill out the short feedback form at the end of the presentation, that would be greatly appreciated. I will now turn the floor over to Hansjoerg.
Thanks, Emily. Hello, good afternoon, good evening, good morning, ladies and gentlemen. I'm very happy to present this very interesting topic on the opto-electronic S-parameter measurements on optical transceiver and receivers. Hopefully with this webcast, we can give you an insight on how to do these measurements on fiber optic components for high-speed and medium-speed fiber transmissions. Where do we actually have all these applications? Well, in fiber transmission, we basically consider two different application spaces, which are one on the telecom side, ranging from medium to long distance transmissions, and on the other side, we have the datacom field with basically short read interconnects. These two fields basically are distinguished in, I would say, three dimensions. One is the frequency dimension, which is basically this class of speed. The other one is the wavelength dimension, which is basically short wavelengths at 850 nanometers, and then the 1550 or 1310 nanometer ranges. The third dimension is the kind of fiber employed. For the telecom ranges, it's entirely single-mode fiber. For the datacom range, it's both multi-mode and single-mode fiber, and this is basically determined by the distance to bridge. So the 850 nanometer range is basically multi-mode, and in the 1300 range, we have both multi-mode and single-mode fibers. The speed classes are basically determined by the application. So in the cable TV, and the fiber to the home, or the radio over fiber, or some people also call it radio frequency over glass, this field is mainly dedicated to the lower speed class below 4.5 gigahertz. When it now comes to the Ethernet, gigabit Ethernet transmission ranges for datacom, it's mostly in the 10 to 20 gigahertz range, addressing 10 gigabit or 17 gigabit fiber channel application. When it really comes to very high speed, to long distance transmission, now it can really comes to the 40 gigabit, and recently all the standards all go to 100 gig. So we have the 40, 100 gig modulation speeds, and here they really employ new modulation techniques like complex modulation, employing both amplitude and phase information. And for the medium reach connections at 100 gig, here's a massive way into parallelization, massive parallelization by employing multiple wavelengths around 1300, or even multiple fiber lines in forms of parallel fiber interconnects. Also for the interconnects, there's also a very strong trend to really introduce more and more optics into interconnecting regimes, which were traditionally only occupied by the electronic domain, which are, for instance, chip-to-chip interconnects or backplanes, or even what we see in the latest streams like of the Intel Interconnect Lightpeak project, where we have interconnects, short-reach interconnects, which really interconnect peripherals, external peripherals, via optical fibers. Now, when we really discuss the value chain for optical components, opto-electronic components, we really start on the very left side, where we have basically electro-optical chips. These chips consist of, for instance, pin diodes, amplifiers, and these all have to be packaged in a very simple way, just packaging on a submount, or into very simple packages like the receive optical assemblies or transmit optical assemblies. And in a further higher degree of integration, those are then integrated into higher complexity modules. And then further on, they move on for line cards, and even at the final end, they move on into network elements and systems. And all these different, in these different stages along the value chain, the measurement requirements really change. At the very end, in the network element range or on the line card range, we have very complex measurements. And these complex measurements are very application specific. Just imagine you want to measure the bit error ratio of a transmission line, and you really do this on the component level to characterize the performance of the component. But on the very left end on the value chain, at the very beginning, you really do only basic measurements which are not really application specific. You're interested in basic performance features and characteristics of your components, for instance, a bandwidth measurement or a return loss measurement. When you do all these measurements, it's in a medium range of the value chain. Sometimes you want to identify which of the measurement performance characteristics really come from the component itself, or maybe what of the characteristics comes from the packaging around the component. So it's really important to be able to distinguish between the real component and the parasitics, the externals. When it really now comes to, sometimes you have an issue, and you do this, you detect an issue in a more complex kind of measurement, like if you do a bit error ratio measurement, and you want to identify where, for instance, an increased bit error ratio comes from, then you sometimes need to find ways to really dig into the component and find out the real issues that are associated with this component. Here, for instance, is a nice example, and I will come back to this example at a later stage in the presentation. You have a very nice and clear optical eye. This is a 5 gig eye with a very nice extinction ratio, clearly open. But then when you see the eye that you have received at the output of your receiver, then it's really distorted. And the question is, where do these distortions come from? There's an eye closure, and the eye closure is not really by noise. It's really kind of a systematic error in the eye. And where does this come from? Is it bandwidth? Is it some other effects? And later on, we will find some clues on this, on the root causes, and especially how the optoelectronic S-parameter measurements can help you find the root causes. Now, after this introduction and the problem statement, I will give a brief introduction into the theory of the electro-optic S-parameter measurements. I will define the measurement parameters. I will give definitions on S-parameter measurements, and then I will also explain the Lightwave Component Analyzer principles and the concepts behind that. And then I will show application examples, measurement examples in various ranges of this matrix. I'll start with cable TV and fiber to the home receivers and transmitters. And I will talk about on-wafer measurements on very high-speed components. Then I will address the very interesting range of the 10 to 20G Ethernet components. And finally, I will also show a little bit about 40 to 100G modulator characterization. Now, key component specifications. What do we really want to measure, and what are possible root causes if the measurements show some imperfections? Well, the key component specifications are basically you want to know what is the bandwidth of your component. How flat is the bandwidth? How flat is the frequency response of this component? Especially also, how good is the conversion efficiency? How good is the gain of your component? And finally, if you introduce it into complete electronic circuitry, for instance, how good is the return loss of your component? And if you really look at these different factors, if they are not perfect, what could they actually do? For instance, an amplifier bandwidth and the flatness imperfection really might limit the system speed. Then if you have a preamplifier which has a very bad matching to the laser, then you really have some reflections and really also have an impact on the clarity of your eye. Also, if you look at the laser or a modulator or even a photodiode, the operation and the performance of these components are very much dependent on the biasing conditions of these components. For instance, a photodetector is not properly biased, has neither a large bandwidth, and also it shows saturation effects at high optical input powers, which then really decrease the effective and useful bandwidth. So all these different components and these different effects you really want to measure, and one way of doing these basic measurements is through the optoelectronic S-parameters. Well, optoelectronic S-parameter measurements really lead you to a way in order to identify components and the individual contribution of a complete transmission link. For instance, in this example here, we have, for instance, a transmitter, which is a combination of various individual segments combined with a fiber, and then you have a receiver. And if you look at the outcome of this signal, you see it in the time domain. This seems, for instance, this behavior. But if you want to now really go back into individual responses, it's very hard to distinguish between the individual contributions. In time domain, the overall response is a concatenation of the individual responses, and the concatenation is basically by a convolution of the individual responses. Now, in frequency domain, the equivalent is not a convolution, it's a multiplication of the individual responses, and therefore, in order to separate the the overall response into individual responses, it's much easier to do that in time domain because multiplications can be very easily divided up into individual responses. Therefore, an analysis in the frequency domain is much, much easier than in the time domain. Now coming to a few definitions of optoelectronic component S parameters. Basically, if you have a transmitter, the transmitter is characterized by two essential S parameters. One S parameter which basically describes the conversion efficiency from the electrical to the optical domain is the optoelectronic S21, the forward transmission factor. But you also have in a transmitter, you have the electrical return loss. On the receiver side, it might be a photodetector, it might be an integrated photodetector plus preamplifier. You also have the forward transmission, which is the conversion from the optical to the electrical domain. And similarly, as in a transmitter, you also have the electrical return loss. Similarly to all optoelectronic components, and commonly they do not have a reverse transmission. There's no S21, never. So if you look at the typical S parameter measurement here, we have this for a detector. You see the S21 for a detector, and you see here the absolute responsivity over frequency. So the evolution over frequency, how the absolute responsivity decreases because of the limited bandwidth of this component. We were interested, for instance, in what is the 3 dB bandwidth. So that's basically the roll-off by 3 dB from a low frequency start point. You're also interested in how much is the gain peaking of this component. And if you just look at the how well this is matched to some driving or some receiving circuitry, you're really interested in the impedance matching. But not only for a complete characteristic of a component, not only absolute and basically the amplitude characteristics are important, it's also important to be able to know about the phase response of such a device. Phase response shows up in group delay information, and group delay information is also very important, for instance, to judge the balancing and the balance of multi-port electrical devices. Now let me come to the conceptual diagram of a Lightwave component analyzer. Well, a Lightwave component analyzer measures the optoelectronic characteristics, which basically always one part is the electronic and the other is the optical, and it's a conversion between those two worlds. So a Lightwave component analyzer is a measurement instrument which measures small signal amplitudes based on sinusoidal signals. So you have in the lower part here, you have basically the diagram of an electrical network analyzer, a microwave network analyzer, for instance, where you have a synthesized RF source which produces a well-known well-known signal in terms of amplitude and phase, and you have a normal reference receiver for microwave signals. But then for the optical domain, you have a Lightwave source which converts the RF signal in a very well-known way, in a precisely calibrated way, into a well-known optical signal which has exactly defined amplitude. On the receive side, you have a Lightwave receiver which then converts the received optical signal into a well-known electrical signal. And by comparing now the sent signal with the received signal, then you can actually determine the characteristic of a component. So with the cross segments that you have here, you can actually calculate different ways and different measurement modes. For instance, you have an O2E mode, which basically means you have a defined optical signal and you stimulate a receive device like a photodetector, and this produces an electrical signal, and you measure the electrical response signal, and from that you determine the transmission characteristic of the device under test. Here's a few examples of devices under test for these different measurement modes. For the E2O measurement, that means an electrical stimulus and an optical response. This is typically a modulator device or a laser device. And here, for instance, you have an explanation of the responsivity of this device. For instance, for a modulator, you have usually, if it's a lithium niobate modulator, for instance, you have this characteristic, this cosine square characteristic, and you operate it usually in a bias point, which is at the point of the maximum conversion. This is the quadrature point, and here you have the conversion of the electrical signal in the optical signal, and the conversion is optimum if you are right in the bias point, but if you move away from the bias point, the conversion gets flatter and flatter, and therefore the conversion efficiency decreases. So it's important to set the right bias point of this component. Similarly, for a laser, you also have a bias point which is determined by the average injection current, and you modulate around this and generate from a small signal electrical modulation, a small signal optical modulation. On the receive side, similarly, you have the characteristic for a photocurrent, which is proportional to the incoming optical signal, and here also on a certain bias point, you have the conversion from the optics to the electrics. Also, last but not least, you can also make measurements of pure optical components. The question is, does this really make sense? But indeed, it really makes sense. For instance, if you want to measure fiber optic cables to a very precise length, it's important to determine not only the loss but also the length of the fiber piece. And for instance, this is determined by the group delay of this piece of fiber. The building blocks of an LCA are basically, as I described, a network analyzer, and the second important block of such a network analyzer, for instance, is you need to calibrate the electrical connections between the network analyzer and the device under test. And the third important building block is the Lightwave Component Analyzer test set, which is basically consists of a transmitter and a receiver. And what you actually see is a network analyzer makes always a measurement in the electrical domain, from electrical to electrical. And if you have a device under test, which is, for instance, a receiver, then you always have two conversions. You have one conversion from the electrical domain to the optical domain, and the optical domain to the electrical domain. Here again, we have the concatenation of individual responses of a transmitter and a receiver. And later on we will see that it's important in order to identify one of the two responses, either transmitter response or the receiver response. It's really important that you have to be able to extract one of the individual responses from the overall response in order to identify, for instance, the response of the device under test. Let me show you a little bit more about the details of such a Lightwave Component Analyzer. As I said, the Lightwave Component Analyzer on one hand consists of a network analyzer, a microwave network analyzer, and this is tightly connected to an optical test set. Tightly connected means there's a connection of RF cables into the test set, and the RF from the network analyzer is then actually either then to an internal reference transmitter, or it's moved out in order to connect to the device under test. For the reference transmitter, we usually use lithium niobate modulators because they are a very stable component. They can be modulated at highest frequencies, and they can also operate it across various wavelength ranges. On the receive side, you have a photodetector, which is a wide bandwidth photodetector, which is also very broadband in terms of optical wavelengths. And it's also important that this photodetector is capable of handling very large optical input powers. Now I'd like to exploit a little bit the concept of de-embedding and fixturing, which is a key feature that all the network analyzers provide. As I said before in the introduction, the network analyzer always measures in the electrical domain. And since the overall chain is always the conversion from the electrical to the optical and from the optical back into the electrical domain. So it's always important, if you have an E to O device, really need to de-embed and to extract from the overall response the characteristics, for instance, for this reference transmitter. But it's not only the reference transmitter that needs to be de-embedded. In many, many applications, and I will show you two examples later on, you also have adapters which connect between the measurement system and the device under test. This can be a fixture, for instance, for impedance matching. It can be a wafer probe, and it's also important to really be able to de-embed this fixture and this adapter from the overall measurement. Now let me come to the examples, the measurement examples that I'd like to show you. I will start with the cable TV or fiber to home node, and will show you some of the basic measurements that we will have, which are, I would say, representative for any opto-electronic component. So it's basically, we have here a measurement for the return path transmitter or for the downstream receiver. We have basically a bandwidth measurement, that's the S21 measurement, and we have a measurement not only for the bandwidth, but we also have a measurement for the overall conversion efficiency. But we also have a measurement of the return loss, and this return loss basically represents the impedance matching for the optoelectronic component. Now let me address here a few specifics to the cable TV world. Cable TV world, you might know that, is basically a 75 ohm world. But on the other hand, the RF world is really a 50 ohm world. And now you have to mate these two worlds, and it's important that you make this mating correct, that you do not have an impact of this adapter on the measurement results of your device under test. Typically, what you can use is a so-called minimum loss pad, which is a fairly good adapter between the 50 ohm world and the 75 ohm world. But also the cable TV world also uses different kinds of adapters. The network analyzer world is in this speed class up to 4.5 or 8.5 gigahertz is a world which uses N connectors, but the cable TV world basically uses F connectors. So you have adapters, and you need to actually de-embed also these adapters. The de-embedding can be done with some tools that are available in several network analyzers. There's tools to be able to characterize those adapters. Those adapters, For instance, here you have a minimum loss pad, and this minimum loss pad then can be characterized by this adapter method, adapter characterization method, by a short open load measurement. And you, from this adapter characterization, you get an S parameter file, and this S parameter file can then be loaded into the fixturing application of your network analyzer. And by this loading into the fixturing application, you can actually then extend the 50 ohm N-type calibration plane into the F-type 75 ohm calibration plane, and then you have actually extended the calibration plane directly to the input interface of the device under test. The next slide shows how well this works. For instance, this is an S11 measurement, or return loss measurement, which really compares the de-embedding and the fixturing application approach with a calibration entirely to the device under test interface, and really this shows a fairly well matching of the two approaches. So this allows you to basically employ the 50 ohm calibration and extending the calibration plane to the device under test by de-embedding of this adapter in form of a minimum loss pad. Now, let me move on to another example where you really need to de-embed the connection to the device under test. On LCA measurements, this of on-wafer components, the challenge is really to be able to parasitic-free contact the device under test. Here, for instance, on this photograph, you see a wafer of top illuminated photodetectors, and you see here the fiber tip, which you actually move onto the fiber, onto the pin diode, and it's important to be able to not only remove the impact of such a fiber probe, but the most important effect is achieved if you can properly remove the impact of the wafer probe. Usually, if you do calibrations, the calibration is to the coaxial interface, but then you actually need, again, to extend the calibration plane to the plane where the probe tip connects to the device under test. Here we see such a configuration, and as I described, for either way EO and OE measurement, you need to extend the coaxial reference plane through the RF probe onto the on-wafer reference plane. Similarly, it's also important that you be able to expand the optical reference plane at the output of the LCA test bed onto the tip where you connect the optical probe to the device under test. And again, here it's possible to employ adapter characterization techniques and de-embedding fixturing applications for wafer probes. On this photo here, you see actually a set of reference substrates which you use to characterize the wafer probe. So typically, the procedure is that you have one-port calibrations performed consecutively, one after the other, and use these different calibrations together with an adapter characterization macros that, for instance, we have implemented in our network analyzers, and then as a result, you receive an S parameter file for the RF probe, and this S parameter file you can then use in the fixturing application to de-embed the wafer probe. Similarly, you can employ the same principles for an optical probe. Optical probes can also be characterized by key factors like the length of the probe, the fiber length of the probe, together with the refractive index. You can also use this the attenuation of the probe. That means basically the attenuation which is determined by the fiber-to-chip coupling, or you can even use the S-parameter file of such a piece of fiber. This slide now shows the result of properly de-embedding the wafer probe, and it effectively removes the measurement ripple from such a measurement. This is a very high-speed photodetector, and here you see for the return loss measurement, it's an unmatched. Therefore, the return loss is basically 0 at low frequencies. And you really see that on the green curve, the wafer probe is, the impact of the wafer probe is effectively removed, whereas in the yellow curve, you really have still the big issues of the reflections by the wafer probe. Similarly, also in the S21 characteristic, the blue one is effectively removing the effect of the wafer probe. Also, in removing the wafer probe also means extending the reference plane, and that means actually extending the reference plane also removes the delay, the transmission delay imposed by the wafer probe. You will see, for instance, here in this the pink one is the pure diode measurement, and here one is the pure measurement exposed through the wafer probe, and the difference is basically the delay of the probe itself. Now let me move further on into characterizing 10, 20G transmitters and receivers. Here, basically, in this field, we have directly driven lasers for the transmitter components, and here the key challenge is that the frequency response of these lasers are bias dependent, so the effective bandwidth and the relaxation frequency of those laser components really depend on the biasing conditions. Therefore, it's important to be able to judge on the internal characteristics of such a laser, on the evolution of the relaxation frequency over the average emitted optical power. Also, if you want to judge about the expected time domain performance, it's also important to be able to get an idea based on frequency domain measurements. Here, for instance, you can actually use the transform features of network analyzers to convert from the frequency domain into the time domain. And the basis is that you have a frequency response measurement which has both a precise knowledge about the amplitude characteristics and the group characteristics. And from this, then you can calculate, or actually have the network analyzer calculate, the impulse response or the step response. And here, based on the amount of overshoot in the frequency domain, you see also the amount of overshoot in the relaxation oscillations. So this gives you a very first and rough insight on the digital and the time domain performance of your component. Now let me come to another very big challenge, especially for these gigabit transceiver components. All those components are essentially balanced devices. What means balanced devices? Well, balanced devices usually have one optical input or output, but multiple electrical ports. And if you have a traditional network analyzer, which usually has one electrical stimulus and one electrical receive part, then you can only connect one of the two electrical ports. But basically, these balanced devices, they really, in the usual use case, they need to be operated with two electrical ports. And therefore, the challenge is, how can you make these S-parameter measurements in a way that you can simultaneously connect both electrical ports and also analyze these components with respect to the behavior in relation to the two electrical outputs or two electrical inputs. We have here, for instance, a few examples. One of the most common is a receive optical assembly, which consists of a pin diode connected to a transimpedance amplifier which drives two electrical output ports which are actually operated in push-pull. But on the other hand, also on the transmit side, we have a transmit optical assembly, which is basically a VCSEL device, a laser device. And usually we would expect that a laser is always connected on one side to the ground, to case. But for those components, in reality, it is not. But in contrast, both the anode and the cathode are connected to the hot interfaces of the electrical inputs. For the complex modulation, very advanced modulators, also those are also operated in push-pull operation, essentially to reduce the overall drive level, but also to impose both I and Q modulation for QPSK signals, for instance. Now, such a configuration here is basically for differential components is realized by multi-port electrical network analyzers. And here we have a setup for characterizing a receive optical assembly, which consists of a pin diode plus a TIA. And here we are basically interested not only in the single-ended gains of such a Rosar, but also on the transimpedance of this device, but also on the differential gain and how well the common mode rejection behaves in such a device. For the transimpedance, it's also important that you be able to characterize the photocurrent of the detector, because the photocurrent basically determines or is an input parameter for the conversion efficiency of the pin diode, and in combination with the feedback resistor, you then can calculate the transimpedance gain of the complete assembly. Here what we have is a few examples on a Rosar measurement. In the upper part of the graph, you see the typical return loss of the individual electrical ports. And here you see the differential efficiency, which is actually the combined efficiency of the push-pull operation of the both output interfaces. So the network analyzer basically calculates the differential efficiency based on the individual responses. So that's actually the S21 and the S31, and from those calculates differential efficiency. But if you really want to know the performance of this component with respect to the balanced operation, the push-pull operation, you can actually then calculate the common mode rejection, which is then normalized to differential efficiency. And here, if you look at the individual responses of the transimpedances, you really see here an imbalance, which really results into a straight, strong decrease of the common mode rejection of this device. And another important measurement for the opto-electronic components is how does this component behave if you have very large optical input ports. The TIAs for the receive optical assemblies have to handle very large input power ranges. And here you see an example where at small input powers you have a very large transimpedance, but as you increase above the input power above minus 11 dBm, the saturation really begins to start. And the saturation really can also not only be seen in the small signal response, but it can also be seen in pattern distortions in the time domain eye diagram analysis. Now I want to come a little bit back on the time domain issues that I showed in the introduction. We had this, remember, we had this transmitter eye, which was clearly open, and the receive eye was fairly distorted. Now if we look again in the frequency domain analysis of this device, and we just look at the responses, the individual responses, the S21 characteristics, they really seem to be fairly nice. But if we now really look at the differential response, then really see a strong reduction in the overall bandwidth and really a breakdown of the transmission characteristic. And you can wonder where this comes from. And if you now really look at the time domain conversion of those responses, you really get the clue. The clue is that you have in the output ports, you have a very strong imbalance, and this imbalance basically determines that you have this strong decrease in the overall differential gain characteristic. You can also look at the individual eyes. You just resolve this, and it's really clearly seen that this delay of the 38 picoseconds is really the delay between individual eyes. And if you combine those, then it's a clear explanation why the green eyes are so bad. Now at the end, let me come to the last example, the 40 and 100G modulator. 40 and 100G modulators, especially for the new complex modulation formats, they are all operated. Usually they have two or four electrical interfaces, and always two of those four are operated in push-pull. And those complex modulators, they are basically consist of two individual modulators, which are then modulated by different bit streams, and those two different bit streams combined, then they realize the constellation map for the QPSK modulation. So for this external modulator, it's also important that you have, for instance, the transmission characteristics of the individual driver amplifiers to the modulator, that they are well matched. They are well matched in amplitude and also in phase. This last example that I show is a very early measurement of a combination of a lithium niobate modulator, which has actually is a QPSK modulator, and in this example, it's driven by two driver amplifiers, and you really see that the two characteristics of the individual combinations of the amplifier plus the modulator, they are fairly apart, and also this shows that the common mode rejection is not very perfect, and further analysis and applying these tools really allows you to optimize the bias conditions on the modulator, the bias conditions on the driving amplifiers. Now let me, before concluding the whole presentation, I'll show you that Agilent provides a number of different solutions specifically dedicated for the application spaces within the Lightwave Component Analyzer family. There's a class of Lightwave Component Analyzers centered around the economy network analyzers, mainly addressing the lower speed classes of cable TV and fiber to the home radio over frequency components. The gigabit Ethernet class is mainly addressed by the 26.5 gig PNA-X series network analyzers, and there's two options addressing either the single mode transceivers or the multi-mode transceivers at 850 nanometers. For the very high speed class of optical components, there is the high-end Lightwave Component Analyzer based on the 67 gigahertz network analyzer, and shortly we'll be releasing a version which is based on the new 50 gigahertz PNA-X network analyzer. So you can also in future address balanced devices in the 50 gigahertz class. The principles that we employ for our Lightwave Component Analyzers is that we keep the basic network analyzer functionalities and all the features of the network analyzer unchanged, and we just add a very simple configuration of the Lightwave Component Analysis function. And after this configuration, the network analyzer is still operating, and the LCA is still operating like a network analyzer. So you basically only configure the wavelengths that you want to use, the optical power that you want to send to your device, and then you can also employ de-embedding features, for instance, like de-embedding the wafer probes, the optical probes in an optical path de-embedding. But more importantly, you can also very simply use the S-parameter files for electrical probes, like a minimum loss pad or a wafer probe, into this setup, and then the Lightwave Component Analyzer automatically fully de-embeds and removes the impact of those adapters from the S-parameter measurement. Now finally, some of our customers always ask us, why do you need such a complex system? Can't you just use a network analyzer and add a photodetector to make a transmitter measurement? Well, in principle, this is true, but it's very important that you have traceable and reliable accuracy, and this is basically that we, in our calibration, we all trace it back to absolute standards, and the absolute standards, that's what we use from NIST, from the National Institute of Standards of the US, and we have these absolute traceable standards where we relayed our calibrations and our specifications to those absolute standards. Now concluding, I've presented the concepts of fixturing and de-embedding, plus the usage of optical transmitters and receivers for known characteristics to realize a network analyzer or transform a network analyzer into an LCA. I've talked about the de-embedding principles to be able to de-embed parasitics, mainly related to connecting a measurement system to the device under test. Time domain analysis based on frequent domain measurements really gives you an insight on a device under test digital performance. And finally, balanced measurements and the base balanced measurement capability for optical and electrical multi-port devices under test really gives you a very nice insight in the performance of future 100G transceiver components. Before really finishing, if you're interested in more information, you just search for LCA on our webpage, and there's two application notes which basically describe the principles of optical component analysis, small signal S-parameter measurements of opto-electronic components in the 101. And then we have a specific application note dealing with how to set up the measurements for on-wafer testing. And the next live demo of the Lightwave Component Analyzer will be on the fiber optic exhibition in January 2010 in Japan. Now, before really concluding, I'd like to target you to the two different sets of webinars. The first is the webinar on the digital applications, and we also have webinars talking about photonic applications. The last one slide here is that we will have another webinar coming up on the Photonic series, which is dealing about polarization challenges in 40 and 100G networks and network upgrades, and this will take place on January 27 of 2010. Thank you very much for your attendance, and now I'm open for a few questions.
Great, thanks, Hansjoerg. Now, I'm not sure we had too many questions. Oliver, did you say you did receive a couple?
Yes, I got a couple of questions. The first question was from a participant who wanted to know if the instrument can measure laser performance parameters like RIN, relative intensity noise, or mode hopping, for example. Hansjoerg, can you say some words if we have these capabilities?
Well, basically, yes. A network analyzer is always has a calibrated receiver which can measure, also can operate like a spectrum analyzer. But actually, we have an excellent solution already in place, which is a solution which consists of a spectrum analyzer with a dedicated, calibrated opto-electronic front end, which is the RIN solution, the N437xB, and this gives you an excellent insight on that. And for the other question was, sorry, Oliver, what was that again?
The participant wanted to know how we can, if we can measure also mode hops with this instrument.
Ah, okay, I see. Yeah, mode hops. Well, mode hops, if they turn up in the electrical domain, especially in noise effects. But if you want to look beyond the noise effects, then it's also with the optical modulation analyzers, the 4391A. There's also ways in be able to detect those mode hops, and by looking at the refined or high precision optical spectrum and a very high resolution spectrum feature, and then you can analyze the mode hops and the spectral changes on your device under test.
Okay, thank you, Hansjoerg. Another participant wanted to know what happens if, so we have the network analyzer, or the LCA consists typically of two parts of the instrument, the network analyzer and the receiver part and the transmitter part, and they are connected together. And one participant wanted to know what happens to the calibration if one exchanges the network analyzer with another one and moves with it also the calibration files. Does this have an impact?
Well, basically, there's two answers to that. Basically, we specify our Lightwave Component Analyzer as a system. And the system consists of two components, which is a network analyzer and an optical test set associated to this. And those are calibrated together. This is how we specify in order to be able to be fully traceable and have guaranteed specifications. In reality, we have enough confidence that by properly employing electronic calibration methods, and the electronic calibration is basically determined by the electronic calibration that you do on the electrical interfaces of the LCA, that you can then basically be independent of the network analyzer. And therefore, it's possible to exchange the network analyzer or change the network analyzer and the Lightwave Component Test Set. But you always, when doing this, you must be sure that you move the calibration data which are associated with the optical test set with the network analyzer.
Okay. Do we have a question? Time for one more question?
Yes, let's do one more. And just before, I know that it's at the end of the hour, but just a reminder that there is a short feedback form that will pop up when you exit the WebEx. Let's answer the one more question, and if you do have any more, please feel free to email Hansjoerg directly. Thanks again, everyone, and have a great day. Sorry, Oliver, do you have the last question?
Okay.
Yeah, okay. I was not sure if we are ended now or not. So, Hansjoerg, I have one question that came up very certainly. So, one participant wants to know, he's especially interested in the S12 measurement. You mentioned that is not really present in an electro-optical component, and he mentions if someone wouldn't have an S21, wouldn't we have an S21 if some of the input of the receiver is reflected back down the fiber optic cable transmission? So doesn't a reflection act as a kind of S12? Can you say some words to this?
I would not consider it an S12. The overall transmission performance is depending on external reflections. I think you probably refer to reflections that consist between the optical output interface of the device in the test and for instance, the optical input into another component. So you have you have forward and backward reflections. You have actually like a small interferometer or an echelon in these. And this is like a concatenated component after the OE component, and this effectively determines the overall transmission performance, but it has no feedback to the input interface of the OE device. That means, therefore, the return transmission in that is not possible. It would, for instance, be the case that imagine a laser would emit part of the light back into the electrical domain. That would be like a laser would act like a detector, or a detector would emit part of the light, and that's actually not possible.
Okay, thank you very much. There are no more questions up to now.
Okay, great. Thank you. Thanks again, Hansjoerg. Thank you, Oliver. Great presentation, and thank you to everyone for attending today. Hope you have a great remainder of the day.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.